Birth and death chains are a class of Markov chains that you encounter very frequently. The state space is the set of integers, and only some transitions are allowed. So if the chain is at an integer I, then at the next stage only 3 moves are allowed. It can go up 1, stay in place, or go down 1. The move up is called a birth, the move down is called a death. You've seen numerous examples of these. The simple symmetric random walk is one. The Ehrenfest model that you've seen in examples is another. It's a big class, and it has a wonderful property, which is that the detailed balance equations are always satisfied if you have an irreducible birth and death chain. And so we are going to restrict, as we've done throughout, to finite states, so finitely many integers, irreducible, and why don't I throw in aperiodic for good measure. So if you have a birth and death chain that satisfies these conditions, and actually many that don't as well, these have detailed balance. And as you know, if they have detailed balance, then you can solve the detailed balance equations, and the solution is the stationary distribution. So you have a quick way of getting the stationary distribution pi. Now, to see why they have detailed balance, notice, well, actually, why don't we write down the detailed balance equations that says that for any two states, I not equal to j, you have pi I pij is pi j pji. For birth and death chains, almost all of these equations are simply 0 equals 0, because, I mean, for example, you can't go from the state 5 to the state 10. You can only go to 6 or 4. So for most I not equal to j, these are 0 equals 0. And so they're interesting only if I and j are separated by 1. And in that case, if I and j are states and they are separated by 1, then both of these transition probabilities have to be positive. And that's because the chain is irreducible. So if 4 and 5 are states, then the only way you can get to 5 is via 4. And the only way you can get to 4 is via 5. So both of these have to be positive. And in that, so then you have, I think without loss, we can write pi I p I. Now I won't write a generic j, I'm going to write I plus 1. Okay, because you can't go there. That has to be equal to pi of I plus 1 and I said it has to be equal to, but in fact our job is to show that that's satisfied for every single I. Well, we've just said that the transition probabilities there are positive, so you can write pi I plus 1 as pi I times Right, so you can rewrite the detailed balancing equations in this way, and now you ask yourself, well, is this satisfied? Yes, sure, it's satisfied. You see, you know the transition probabilities. So you know this ratio. So you can simply start at any point and start building the vector pi by multiplying by these consecutive ratios. You can either move up the way we're doing here, or you can move down if you prefer. But you will end up solving the detailed balance equations, because the chain will not loop back around on itself or do a wild leap. It's just going to go from one integer to the next integer. And the point of this is that if you have a birth and death chain, and you've checked that it's irreducible, you've checked all the conditions, then you know without any further checking that the detailed balance equations are going to have a solution, and that therefore that's the way you should go about finding the stationary distribution pi.